to Lecture 6 of the Compton series. Today's topic will be heat engines and transportation. So let's begin with a quotation from Sadiq Carnot, who said that the study of these engines is of the greatest interest. Their importance is enormous, their use is continually increasing, and they seem destined to produce a great revolution in the civilized world. So the term is 1824 Reflections on the Motive Power of Fire. After today's lecture, if you're interested in reading more about thermodynamics, I'd recommend the book Mere Thermodynamics by Don Lemons, and heat engines in particular. If you'd like to know more about transportation and statistics about transportation in the US, I'd recommend the DOE Oak Ridge Transportation Energy Data Book. If you'd like to know more about the physics of transportation and some future prospects, I highly recommend the American Physical Society's Energy Future Think Efficiency report. And I'm happy to give people web addresses to those at the end.
Will this be available on the internet?
It is. I could print some copies, though. So, why might you care about thermodynamics? I have to say that it's one of the least favorite topics of most physical scientists. We've got a lot of engineers, physicists, chemists. A lot of us don't like or didn't like our lessons on thermodynamics. So why might you spend the time to go through the details here? Well, first of all, it really is a pretty simple theory. And once you understand the workings of it, you can understand a really wide class of phenomena. And this is just to list a few. So you can understand steam engines, gas and diesel engines, magnetohydrodynamic generators, thermoelectrics, thermionics, solar thermal, refrigerators, air conditioning, and perhaps the greatest reward of studying thermodynamics is you get to understand how the drinking bird works. So for the first few slides, I'd like to review some of the physics that I talked about last week and amplify on a few points and redirect some of those toward the idea of heat engines. So as you recall in the last lecture, I introduced this system of three particles. And each particle could have a quantized ladder of energies, so 0, 1, 2, 3, 4, so on. So in this particular case, this particle 1 has 1, this has 3, that has 0, so the total energy of this state is 4. Now, what we did last week was then distribute different amounts of energy in the system. And recall that if we have 0 energy to distribute, then there's only one way to do that, namely that all the particles have 0 energy. If you have 1 unit of energy to distribute, well, you can either put it on 1, 2, or 3. So there are 3 different ways to do that. If you have 2 units of energy, there are 6 different ways to distribute it among these 3 particles. You see that this very rapidly increases so that when you have 14 units of energy, you really have a large number of combinations to distribute across. If you plot this among up to higher energies, you see that, say, at 200 units, you have something like 20,000 different combinations with which you can distribute the energy. So this was just 3 particles, but now if you imagine some of the quantities in this room, like 10 to the 23 particles in some volume of air, and you imagine macroscopic amounts of energy, you can see that you're really dealing with a vast number of combinations. So the way we count those combinations is this quantity that I introduced in the last lecture, this entropy, which is just a proportionality constant times the log of the number of those accessible states. And a natural question to ask, so you know that over here, when you add energy, you increase the number of accessible states, so you're increasing the entropy of this little system. So you can ask that question more generally with thermodynamic systems like volume of air. And as I explained last week, the relation between the amount of heat you add and the change in the number of accessible states is just given by this proportionality constant, the temperature. So you might think of the temperature as being a real thing, something feels hot, something feels cold. But it also tells you how to relate a given amount of heat over a temperature to the number of accessible states you add to a system. So this was all a little bit abstract, but we can think about this in a practical setting. So here we have some ice water in a hot room. The room's hot, the ice is cold. And as I said last week, if you have a gradient in temperature, generically you get a current of some type, in this case flow of heat until the two temperatures match. So you know that if water sits out long enough, that its temperature will match the room's temperature. And in the process, some heat delta Q has flowed from the room into the water. So we can now think about this a little bit more quantitatively in terms of that thermodynamic entropy that I just introduced. So again, recall that the change in entropy is the amount of heat you add divided by, in this case, the fixed temperature. So that's a critical point, that the ice is at a fixed temperature. So if you look at the room, if you add some delta, you're taking some heat away from the room at its temperature, so its entropy is decreasing. And if you're used to think about entropy always increasing, this might be somewhat of a surprise to think that the entropy of the room is decreasing, but that's because it's giving up heat. But then, if you look at the ice water, that heat is flowing into the water at 273 Kelvin. So 298 is 77 Fahrenheit, so that's like this room. 273 is 32 Fahrenheit. So that the heat is flowing into the ice water, and the entropy increase there is that same amount of heat over 273. So when you think about the system as a whole, the total change in entropy of the room, which is decreasing, the total increase in entropy of the ice water, you find that because the 1 over 273 is bigger than 1 over 298, the change in entropy is greater than 0. So in particular, the entropy of this universe is increasing. So we can elevate this to a law, which is the entropy statement of the second law of thermodynamics, which says that in a spontaneous process, entropy is increasing. So the kind of schematic here is just like what I showed. If you have hot and cold, heat will flow between them. Entropy will increase until it reaches a maximum, and then here you're at some thermal equilibrium, and nothing happens. Well, yeah.
Is that a direct analogy of potential energy? Other assertions?
That's a good point, actually. So this slide highlights an important difference between those. Yeah. So going back to Joule's apparatus. So in this case, he showed that the potential energy embodied in this mass when it falls is converted into heat in the water in these paddles, so that the energy is conserved. So the mechanical energy of this falling mass is converted wholly into heat energy. But the critical point here is that the entropy is not conserved. So that in the view of entropy, you're adding heat to this water, so you're increasing the entropy in this volume. So while momentum and energy conserved, entropy, even though it's a property of the stuff, is not. And when the second law says it's increasing, perhaps a better sort of verb for that is production. That is, when you add heat to something, you're producing entropy. So if we think about the ice water in the room a little bit more abstractly, so here's the hot room, some T hot, and then here's the cold ice water, T cold. And there's some heat flowing through the glass, in this case represented by this rod. There's some change in entropy of the room, which is the heat over the temperature of the room. And there's some change of entropy of the ice water, which is the heat over the temperature of the ice water. Now, the second law of thermodynamics only says that entropy has to increase, but it doesn't tell you how quickly or to what extent it has to increase. So, in particular, you might imagine that you could siphon off some of this heat and do some useful work with it in such a way that the entropy of the whole system still increases, but just less than in this particular case. So, that's the basic idea of a heat engine. So let's just see how you might do that. So here's the schematic, the picture that in your head. You have the hot temperature and then the heat flowing into some engine, and that produces some useful work. And then that engine rejects some heat to the cold side. And a natural question to ask is how much work you can achieve for a given amount of heat. So you could use this to, say, drive a car or grind wheat or something. So we can think about this in this whole system in the context of the second law of thermodynamics, which says that entropy is always increasing. So sure, you can take work, you can use some of this heat for work, but the entropy still has to increase. So in particular, I apologize for the math. I think this is a pretty insightful derivation. There's more discussion of it in the notes. But it says that the change entropy in the cold side and the change entropy in the hot side is positive. That is, the entropy of this sort of universe is increasing. Now, from the thermodynamic statement, you know that entropy is just some heat flow into that temperature bath. This heat flowing in the cold side of the temperature cold, and some heat flowing out of the hot side at temperature hot. But the difference in this case is that this heat from the hot side doesn't all flow into the cold side. Instead, we're doing some useful work with it. And because energy is conserved, we're taking that energy out of the heat flow. So that means that the Q cold here is Q hot minus the work that you do. So again, the thing you care about is how much work you can get out of this device relative to how much heat energy you have to put into it. So you can solve this inequality for the work out over the heat in. And this is in more detail in the notes if you'd like to have a look. But the punchline is that the work you get out divided by the heat you put in, that's the efficiency of this engine, is always going to be less than 1 minus the cold temperature over the hot temperature. So this really puts an upper bound on how efficient these sorts of heat engines can be. And when that bound is saturated, when this less than is inequality, that is the most efficient engine you can have, the one that can still have entropy increase in the universe, is the one where the efficiency is 1 minus T cold over T hot. Now this was a little bit tedious, but so let's think of what this means. It means that we want the hottest possible source and the coldest possible sink if we want to make an efficient engine. So we want the highest possible temperature down here and the lowest possible cold side, so that the efficiency is as close as possible to 1. And this little bar here just means that this efficiency is the Carnot efficiency. So let's just think about some practical engines. Well, what's the coldest practical temperature that you can use in an engine? Well, most engines just have access to the ambient air temperature, which is 300 Kelvin. This is something like 80 Fahrenheit. And so that puts a lower bound on that. So that's the lowest T cold you can have in a lot of cases. But what's the hottest T hot you can have? Because you might think that you can just operate the engine at much higher temperatures to get higher and higher efficiency. Well, the highest practical T hot temperature you can achieve is around, A bound on this is around 1,770 Kelvin. And at that temperature, if you're combusting your fuels, the temperature is high enough that you can actually, that the nitrogen and oxygen in the air can react and produce these NOx compounds, which are really kind of nasty emissions that you want to suppress in a car. So this really kind of, while you can deal with these emissions, this is kind of a practical upper bound on a lot of engines. Okay, and another upper bound is on material strength. So if you have stainless steel, you would like to keep the T hot, unless you have more exotic materials, you like to keep the T hot less than about 840 Kelvin. So this puts a limit on how cold and how hot a practical engine might be. Now let's think about a practical nuclear reactor. Its T hot may be 600 Kelvin, and its T cold may be the Earth's ambient temperature, 300. So in this case, the efficiency is T cold over T hot, well, 1 minus that, and that's 50%. So the Carnot efficiency for nuclear reactor is typically about 50%. But in reality, so that's the best it can be. But in reality, 30% is a little bit is more typical for how much heat you convert into mechanical work. And obviously, if you convert that into mechanical work, you can very efficiently convert that into electrical work.
The 600K is the water transfer cycle, right?
This is the input steam.
Okay, but the nuclear reactor, of course, it has a much higher temperature. You're going to take
from is from one of these things that has a secondary heat exchange. So
Right,
this is
but what I'm saying is, can't you use another fluid as a heat transfer material that would give you a higher energy?
people do discuss, different, and also for, people talk about helium, liquid metals and things like that.
Right, sodium being one, but you're not going to go into that for more efficient nuclear systems, are you?
I want to talk about that in the next lecture, actually.
Oh, you will?
Yeah, so this is just here I just want to try home the point about these heat engines. So we can elevate these sort of observations to another form of the second law of thermodynamics, which says that a cyclic engine cannot convert thermal energy into mechanical energy unless the device uses two temperatures and discards heat to the cold side. In particular, then it can't be 100% efficient. Another aspect of this is that the fact that entropy has to increase puts an upper bound on how efficient that engine can be. So the picture to have in your head is that you can have something like this, where you go from heat flowing through some engine to produce some work, going up the cold side, but you can't just take heat from a hot side and produce mechanical work with it. So I just want to review a slide related to what I talked about last week, but which reminds you why it is that you have to have two temperatures. So if you just had one temperature, let's think about this system. You have a cylinder and a piston and a mass. And the idea is that you have this hot plate and heat is flowing in isothermally here and causing this piston to rise and doing this useful mechanical work. But the point was, if you want to continue to do work, you have to reset this piston back to this lower thing and then put a new ball on like we do over here. If you only have one temperature, you'd find that to recompress that gas at the same temperature, like in this step, would take the same amount of work you just got out of it. So that in particular, if you ran this as a cycle, you wouldn't get any net mechanical work. So the idea is you really need to have two temperatures and then compress at the lower temperature. And I gave a really schematic picture of how you might do that in the last lecture, but in this one, I thought I would talk about the actual Carnot cycle. And this is a device that if you don't have any friction and you have perfect insulators and so on, you reach the Carnot efficiency. So the idea here is that you have your hot plate and some isothermal expansion that does some useful work. And but then you want to cool that gas down so you can compress it again. So it turns out the most efficient way to do it in this case is to put an insulating sleeve around the cylinder so that none of that useful heat escapes from this hot gas. And in this case, you just let the gas expand and it cools through expansion. Okay, then once the gas is cool, you can put it on your cold side and compress it back down again. And this rejects heat. This rejects heat to the cold side. But then you want to return to this initial state where you have the smallest volume and a hot gas inside. So you do the same thing, the same trick again, where you put an insulating sleeve around the cylinder, and you heat the gas through the compression here. And then now you're back at step one, and you can lift another mass. So this is the sort of idealized Carnot cycle. Now, real engines will have lots of other loss terms. In particular, you can have ways for heat to get from whatever you call your hot side to the cold side, just some piece of metal that leaks heat. And that's just adding entropy to the cold side, and in doing so, you're just losing efficiency. Obviously, if you make mechanical work here, like turning some axle, you can have friction, and that friction is dissipated as heat, and that heat again just flows to the cold side. And that's just entropy that you're producing. So again, you're losing efficiency. You can also have things like some resistance, so that the temperature on the hot side of this engine is actually less than the heat exchange that you're able to access. And that reduces the efficiency. And you also have things like transmitting the mechanical power, mechanical losses, and eventually you get some work out. So you can see why that nuclear reactor wasn't able to achieve its 50% Carnot efficiency, but instead achieved more like 30%. operate between two temperatures. So if you have so a common type of engine is a sort of jet turbine, and that likes to have a very hot high side temperature, and it rejects gas from the jet engine at still very high temperatures. So the jet engine likes to work in a sort of high regime, whereas the steam engine might like to have more intermediate, a steam turbine I should say, might like to have more intermediate temperatures and reject to more like river water, room temperature. So the idea is that even if these engines are restricted between two temperatures, you can combine two of them in this sort of scheme where the rejected heat from one flows into a lower temperature engine, and you can exploit a much wider temperature change. And if you're interested in more discussion of this and some derivation, I put a little bit more technical detail in the notes. But the upshot is that there's a total efficiency for this combined cycle, which is the efficiency of the top guy plus the efficiency of the bottom one, minus the product of the two. So just to put some more numbers to this, if this top guy is 40% efficient, which is pretty typical for a gas turbine, and this bottom guy is 30% efficient, then when you plug those numbers in here, you find that this combined cycle can reach 60% efficiency. So you see that combining these things is really a very reasonable thing to do. And you might think that this sounds so good that you could possibly beat Carnot's efficiency. This sounds quite nice. But it's still the case that if you could build an engine from this hot temperature to this cold temperature, that's still, and the Carnot efficiency would be the highest you could achieve. So even if you can combine a bunch of these motors and get the impression you're getting a better deal, you still can't beat Carnot. And there's more discussion of that in the notes. So this is something you might hear a lot about in the news, this sort of combined cycle. And this is something that's being implemented in a lot of gas generation. And there's this neat article in AMSC that talks about some of the numerics of this. So here's a sort of typical engine that you might use in one of these plants, 330 megawatts, and it's about 40% efficient. And that's this thing here that I said. So this is the jet engine that turns the generator. And this is just like the generator we talked about in the second and third lectures. And then the heat that you reject can be used in the secondary steam cycle. And again, this is just like the generators I talked about in the second lecture. And you see that the hot side of this jet turbine is quite high, and the steam turbine is the one that starts out at this rejected heat. And also more exotic schemes that use magnetohydrodynamic as the topping magnetohydrodynamic generators as the topping cycle and steam as the bottoming cycle. So this type of thing I think is a really neat idea. So for the rest of the lecture, I'm going to move on to transportation engines and statistics about transportation. So let's just go through the steps of how a standard gasoline engine works. So it's ready to start. In the first intake stroke, this valve opens and an air-fuel mixture is introduced by pulling the piston down into the cylinder. This is called the intake stroke. And then as this continues to turn and it drives the piston back up, this valve now closes and compresses that air-fuel mixture. This is called the compression stroke. Now it'll reach this top point, and you'll see that that's as high as this piston will go, and the spark plug ignites that pressurized mixture. And the pressure very rapidly rises at sort of a constant volume. And you can imagine what happens next is that you get the so-called power stroke, and that drives the piston back down. And this is the one that you exploit with the car. And then in a final stroke, the piston rises again, but this valve opens and lets the exhaust escape. So an audience member pointed out last week that you can also think about six-stroke engines. And I won't, because of time, I won't have a lot to say about that, but the basic idea is that you can use steam as an additional stroke here and exploit the remaining heat. And let's just call that quantity R. So I have more of a derivation in the notes if you'd like to see some of the technical details, but you find that in a sort of idealized treatment of this Otto engine, you find that the efficiency is 1 minus the compression ratio to this kind of neat factor. So this neat factor, gamma, is called the adiabatic index of the gas. Now, to go into why that's the case, it's pretty subtle, but what the adiabatic index is it's the number of degrees of freedom in gas plus 2 divided by the number of degrees of freedom. So what are the degrees of freedom? If you have just one molecule running around, or an atom running around, it can move in 3 dimensions. So that's 3 degrees of freedom. If you have a molecule, it can also rotate, and to describe that, you need 2 additional degrees of freedom. So a molecule like N2O2 can have 5 degrees of freedom. So if you plug that in to this index, you find that the index is 1.4, 7/5. Now once you add fuel, you lower that index by increasing the number of degrees of freedom to something more like 1.3. So now we can estimate how efficient some real engines are. So a typical compression ratio in a modern engine might be something like 91, although that can vary. And the adiabatic index might be something like 1.3. And if you just plug that into this equation here, there's the compression ratio, there's the adiabatic index, you find that implies you can reach something about like a 50% efficiency. So it turns out that this compression ratio is really a good proxy. If you work out the details, it's really a good proxy for a cold to hot side temperature ratio, which does reach the Carnot limit. So when people talk about compression ratio, it's really kind of a proxy for what people talk about in these other engines with these temperature ratios. So if you want to maximize the efficiency, what do? Well, you want this to be as big as possible, and you want the octane. You want the adiabatic index to be as small as possible. So if you so the way you maximize the compression ratio is to compress the gas more. But to do that, you need to have a higher octane of the air-fuel mixture, because the octane is what determines how much you can compress the gas before it spontaneously ignites. So you really want to have that gas ignite with a spark plug in sync with the engine rather than spontaneously. So having a high octane allows you to have a good compression ratio. To maximize the adiabatic index, one thing you can do is have a lean air-fuel mixture. That is, you can have more air than fuel, and it brings you closer to this 1.4 adiabatic index compared to 3. Okay, so I think now we have a pretty good sense of the efficiencies of some real engines and terms that go into them. And we can do a kind of back-of-the-envelope calculation to try to anticipate, say, what the fuel economy of a real car is. How can we understand our real cars? So to think about that, let's think about a really simple and stupid car, which is a sphere. And this is my other car. So first let's think of how we want to power the sphere. Well, what are the options? Well, you can use the gasoline engine, the diesel engine, ethanol, hydrogen, nickel metal hydride batteries, lithium-ion batteries. And you'll note here, I'm sorry this is a little bit small, if it's hard to read. You'll note that the energy density of gasoline is really one of the highest at about 35 megajoules per liter. If you compare that to current batteries, you see that batteries really embody much less energy. So for this car, let's be a little bit old-fashioned and use gasoline engine. And this table was from this American Physical Society report, and there's really good discussion of future batteries and improvements. Okay, so just to put that in another set of units that might be more convenient, imperial units, gasoline embodies 114 BTU per gallon, 114,000 BTU per gallon. Recall that a BTU is the amount of heat required to raise a pound of water a degree Fahrenheit. Okay, so the first thing we want to calculate is how much power an engine produces in its primary power. So if you know how many BTUs per gallon, and you know how many fuel is, you know how many miles per gallon your fuel economy is, you can find how many BTUs per mile your car needs to move you. If you know how fast you're going, that is how many miles per hour you're going, you can find how much energy per time, like joules per time, your car needs to move you at a given speed. And just to put some numbers to that, that sort of burn rate power is about 33 kilowatts times your speed in miles per hour divided by the fuel economy. So if you're going 55 miles per hour in a car that gets 30 miles per gallon, this comes out to about 60 kilowatts. So that's about 1,000 60-watt light bulbs. So it's really a significant amount of heat energy. So where's that energy going? Well, obviously it's going into the motion of the car somehow. And, well, why do you need motion to, why do you need power to make a car move? Well, obviously to accelerate it, but also once it's moving, you're subject to drag from the rolling resistance in the tires. You're subject to drag from the air. So for the spherical car, let's just say we only have drag from the air. So the sphere is trying to move through the air, and there's some drag term. So from the lecture on the wind, we reasoned that the force, the drag force from wind blowing on some surface, scales as the density of the air times the velocity squared times the coefficient of drag times the area. But now when you want the power, you multiply by the velocity, so that the power from drag of moving the sphere through the air scales as the velocity cubed. So just to put some numbers to that, this is 5 times 10 to the minus 6 kilowatts times the speed cubed times the drag coefficient times the area in units of feet squared. So these are just convenient imperial units. Okay, so for our spherical car, let's say it's 5 feet diameter, maybe that's big enough to ride in. That drag coefficient times the area of the sphere is 8 square feet. And if you go 55 miles per hour, that drag formula tells you that the power you need is about 7 kilowatts. And now, if you're, so as we learned from the previous slide, the maximum efficiency that you might reach in a practical engine is about 50%. That's taking a compression ratio of 9 to 1 and an adiabatic index of 1.3. And if you're 50% efficient, you need 13 kilowatts. Okay, so if you say, well, if that needs to be my power burn rate, and I want to go 55 miles per hour, you can solve for your fuel economy, and you find that in this particular car, you get 138 miles per gallon. And this is ideal for two reasons. One is that we're at the Carnot limit, and the second is that we're only assuming there's drag, and you're just moving the car against drag. So let's think about a real car. In a real car, you have 100% of the primary energy coming in, and these are the sorts of engine losses I've been talking about. But in addition, you have to have an alternator, a fan, and pumps, and so on. So you lose about 62% of your energy, and then a lot of that energy just goes into standby and idling. So that the amount of practical energy that goes to the drivetrain is about 18% of the primary input. In the drivetrain, you lose about 6%. And then, so that about 12% of the primary energy gets to the actual tires. So how's it used once it gets to the tires? Well, only about 3% of that pushes against drag. About 4% of that is pushing against the rolling resistance of the tires. And the rest of that can be used to accelerate the vehicle. That inertia. And obviously, if you ever want to stop the vehicle, that energy has to go into the brakes. So about 6% of it actually goes into motion. And Amory Lovins, who was here to give a talk last week, made the interesting point that if you think about not accelerating the car, but just accelerating the humans in the car, the fraction of the embodied energy that goes into accelerating humans is really quite a bit smaller. So we were kind of off target by saying that our spherical car is going to get 50% efficiency, so let's use 12% instead, just to put a number to it. If you plug in 12%, you find that our sphere, instead of getting 138 miles per gallon, gets 33 miles per gallon. And you see that that's pretty reasonable. So with a pretty simple argument, we've reasoned through why it is that cars get the sort of mileage that they do. But of course, a factor in this was the drag coefficient. And for us, that was 8 square feet. But some of the best cars are 2 square feet. That's because they're very aerodynamic. And the sizes go up to, say, 26 square feet. So that's something that varies a lot with cars. So this has all been kind of fun, this idealized world. But let's think about how we actually use these fuels in the real world and what we do with all this energy. So this is a plot I'm very fond of, and I've shown it a number of times. So what's neat about this is it shows the primary fuel inputs in terms of the amount of energy that we use from them, and then these eventual points of consumption, residential, commercial, industrial, transportation. I'm sorry, it's a little bit hard to read. And then up here is electrical generation. And again, what's really neat about this graph is that it shows you can just read off the efficiency. So here's the loss from the electrical sector. And if you look at how much you actually have going to consumers, you find that only about 1/3 of the primary energy that's embodied in all these fuels makes its way to the consumers. And you find a similar statistic when you think about transportation and petroleum, that about 25% of the embodied energy is actually used. And now that you know about the Carnot efficiency limit, you can get a sense of why these two numbers are the way they are, why they're about 30%, because that's saying something about the thermodynamics of how we use that heat. So if you'll note that here, this is, we burn this for heat, we burn this for heat, heat. Geothermal is heat. Wind is not heat, but as I said in the fourth lecture, there's still a fundamental bound to how much power you can extract from it. This is hydro, I know it's impossible to read. Nuclear is heat. Solar can also be heat. So you see that the vast majority of how we use our primary energy is in heat engines, and they're all subject to these efficiency limits. That's one reason why I think thermodynamics is so interesting and so informative in this context. So just to recall, so again, a BTU is this amount of heat to lift a pound of water 1 degree Fahrenheit. So the units in this little flow chart from Livermore are in quads. That is a quadrillion, 10 to the 15 BTU. So the annual energy that we used in the U.S. in 2008 was 100 quadrillion BTU. And recall that a BTU is about a kilojoule, and a joule is what it takes to lift an apple about a meter. So you see that 100 times 10 to the 15 times 1,000, that's really that's a remarkable amount of energy. So just as some rules of thumb, about 1/3 of the heat energy input into electrical generation reaches customers as electrical energy. The big factor there is the thermal loss, rather than the transmission. Another rule of thumb is that about 1/3 of the CO2 we emit is in the transportation sector. Okay, so this is the very first slide that I showed in the series with all these different energy scales, but now that we've talked about a few of these in this lecture, we can revisit this and exemplify in a few points. So again, the scale of human exertion, this is, say, an Olympic sprinter. This is the maximum aerobic output of a human. It's about 800 watts, and most people are typically much less than that. And over an hour, that is 3 times 10 to the 6 joules. And then it's informative, I think, to compare that to a barrel of oil, which is 6 times 10 to the 9 joules. So you see there's a difference of about a factor of 2,000 a lot of energy just within the U.S. So if you then think about total energy scales in the U.S. or worldwide in 1 hour, you see that those are about a factor of 10 to the 10 times the amount of energy that it would take for an Olympic sprinter to be utterly exhausted. So it's really a remarkable amount of energy. So going back to cars, an interesting question to ask is how far we drive. And this is a neat plot from the American Physical Society report that shows the cumulative number of miles driven. So the way you read this, for example, is that, say at 80% here, that goes down to about 120. This means that 80% of cars drive less than 120 miles in a given day. It also means that 20% of those cars have driven more than that in a given day. So you can also read off, say, 20% of cars drive less than about 30 miles in a given day. So that means 70% of cars drive more than that. So it's really it gives you a sense of how our transit is distributed. One thing I didn't have a good sense of going into this was what fraction goes to cars and what goes to planes. So it turns out that in terms of the primary energy used, about 80% goes into cars, 10% goes into planes, 10% goes into air travel and pipelines and the like. The thing I was surprised by, this is all from this transportation energy data book from Oak Ridge. The thing I was surprised by is that 27% of the vehicle miles traveled are in commuting. I thought that might be a little bit higher. And the average commuter is something like 12 miles. In their study, they found that 76% of people commute alone, 5.2% take public transit, and 3% walk or bike. This is a national census. One thing which I really had no sense of without doing any sort of quantitative argument was that there's about one gas station per 1,000 vehicles in the U.S. I just thought that was a neat number. So another plot I think is very informative from the American Physical Society report is something that makes the distinction between fuel economy and efficiency. So I've been talking about the efficiency of these Carnot engines, and you might think that you just arbitrary, you can boost the efficiency of these engines and reduce the driveline losses and so on, and boost the fuel economy. Well, if you plot the efficiency of engines as a function of time, you see that it's been steadily rising since the 70s. If you then plot the fuel economy, you see that they departed from each other at around 1985. And so fuel economy is on the left here, and you see that it's settled in at around 27, 80 miles per gallon. And the efficiency has continued to rise. Now, you might think that if the fuel economy were to continue to track the efficiency, that we'd have fuel economies up around, say, even 40 miles per gallon. And indeed, those are the sorts of economies that are reached, the fuel economies that are reached in the EU and Japan. So why is it that the efficiency increased so much, but the economy went another way? So if you look at the acceleration of cars, how fast they go from 0 to 60, and the weight of cars, you see that from the late 70s to the early 80s, the weight dropped enormously. But then since then, it's been climbing back up. So cars have been getting heavier, even though their efficiency has been increasing. They have also been able to accelerate faster and faster. And what this means is we have more power and we have heavier cars, so we're not fully exploiting these gains in efficiency. I'm sure there are many factors, but one thing which I'm sure weighs into this is when you look at the cost of oil during this period. So in 1979, the inflation-adjusted cost per barrel was $106. In 1985, it collapsed to about 50. And you see that's about when these sorts of things depart and the weights increase. So there's a long period of very stable oil prices, and that must have had some influence on our ability to make heavier cars. So it's not just the efficiency or the fuel economy. A further distinction is the energy intensity. That is, how many BTUs it takes to move a person 1 mile. So this transportation energy data book has a neat census of different forms of transportation, and so cars, trucks, motorcycles, buses, and so on. And they find the average occupancy of these vehicles. So if you sample a given car on the road, you might find that it has about 1.6 people in it. If you sample a given transit bus, you might find that it has 9 people. Well, if you know how many people are in a car, what mileage it gets, and how fast it's going, or you don't need to know that, you can find how many BTUs it takes per passenger per mile. Okay? So, as you give an occupancy of a car, you find that they reach about around 3,500 BTUs per passenger per mile. And in 1970, that was closer to 5,000. So you see there's been a real gain in the energy intensity of cars since 1970. One thing that's surprising is that buses are not that favorable in this particular comparison to cars when you just think about their energy intensity. And one thing you'll notice that in 1970 it was better. And I think, although they don't have the occupancy statistic in 1970, I think what this is that more people took the bus in the 70s, so that the energy intensity of that transportation was much, much better. So this is just a reminder that if there is a bus, it's really good you can take it, because when the occupancy factor of a bus is above something like a third, it's when it starts to beat out the energy intensity of cars.
These statistics are only for the U.S.
These are the US, yeah. Yeah, exactly. If you look at Japan, the occupancy factors for the buses are much, much higher and much better than cars. Yeah.
Yeah, the rabbit is in front of what is interesting.
I was worried about that. I can move it out of the way at the end, we can look at it.
So what is the load factor because on the rail?
I'm sorry, he's not
Okay.
I don't remember. That's a bit tricky too, because I don't know what the unit, I'd have to look at the document to see what unit, like it's a real car or a...
Yeah, but I was reading that the rails are not that efficient when you compare with the car, anyway.
Yeah, if you look in this case, Amtrak and Transit Rail do compare favorably to a car, 2,500 BTU per passenger per mile compared to 3,000. So it's favorable, but not... One thing I think is really remarkable here is that the energy intensity of air travel since 1970 has improved remarkably. And a big factor in that is that the efficiency of planes has improved since then. But a factor which I think we're more familiar with today is that the occupancy of planes has also increased. So by packing more people on, we've been able to make planes that are that are more efficient in BTU per passenger per mile than cars.
That will lead to some people that will kill it. Tell that the airplanes are more efficient than the cars, people will kill you. Yeah, I mean, some people are really, really hard on the air travel.
Well, the thing is, though, like if you think about a trip to Europe, in terms of CO2 emitted, it's as if you were to drive a car to Europe, in some sense. So, in terms of a kind of leisurely trip to Europe, that's really a significant amount of CO2, which I think most people. Yeah. And again, another distinction is that it's not just the energy intensity; it's also the impact of the availability of transportation on how cities arrange themselves. So if you have available transportation, you can have higher densities and positive impacts on a community. If you think of, say, DC versus cities or New York or Chicago, cities that have a lot of transportation relative to those that don't, it impacts how people travel. And this is a neat paper where they do a more holistic study and they try to consider those sort of, I don't know what the word is for it, knock-on effects of having available transit. And they find that transit really saves a significant amount of gasoline. So
Per year?
Yeah, that's a very strong argument. Even on top of some of these things about the intensity that transit is very good. So one final fun statistic is two more fun statistics. So this is again from this data book. This is 379 pages of fun. you find that about 20% of it comes from Canada, 10% from Mexico, 9% from Venezuela, Nigeria, of course Saudi Arabia is a big factor, Algeria, Russia, Iraq, Angola, and a large number of smaller contributors. And this is from the Energy Information Agency. And this, it's interesting to note that this varies a lot by country, and we have a much more sort of diverse pie than Japan. So Japan is about 87% of its oil from the Middle East. So it just says different things about our regions. So some of the physics, the thermodynamics puts a fundamental limit on how efficiently you can convert heat into work, and that's the Carnot efficiency. And you can do a little back of the envelope, and there are more details to this in the notes, but you can find the fuel economy, if it's a spherical car, that's pretty darn reasonable in some sense. And you see that these sorts of heat engines, these transportation engines, consume 26 quadrillion BTUs of primary energy. About 13% of that goes into motion. And we use about 100 quadrillion BTUs annually in all forms of energy, in all forms of consumption in the US. And almost all of that is used in heat engines. I'm happy to take questions.
How many pounds of carbon dioxide are produced by the combustion of a gallon of gas?
That's a good question. I don't have the answer on top of my head. We can look it up when I come up.
And do you know what the total CO2 production of this country or the world is?
So I believe transportation is about 2,000 million tons this year. I'd have to look that up before. Yeah.
When we hear the statistics about the U.S. being the energy hog by having a very low percentage of human population and a very high percentage of energy consumption, I'm trying to figure out where that use is greatest. And I mean, some of your statistics on transportation, for example, especially the last one where these large populations are where we were 100 years ago or 70 years ago.
Yeah.
So it's almost like the energy hogginess is concentrated in certain parts of our lifestyle, one of which is obviously you can get in a car and go anywhere you want, anytime you want.
Yeah, it's a factor of the scale. There's so many cars. It's built into how we do
Okay,
it.
so how big a factor is that as opposed to other things that are on your big favorite chart? Where would these all come?
Well, transportation, we use a lot of electrical energy, but the inputs and the efficiency are quite similar elsewhere in the world. I mean, there are places that use more hydroelectric, but we also use, at the sort of use end over here, we use significantly more than a lot of places in the world. So it's really, I don't know offhand, say how transportation and these compare. There might be a table for that. Yeah.
Heat pumps are, I think they're used in Florida for home heating. I think they're window units. But we don't seem to use them up here in the northern latitudes. Do you have any idea why?
That's a good question. Well, so a heat pump is like that thermal cycle in reverse. So you put work in and go from the cold side to the hot side. And I don't know exactly, but I would imagine it's maybe the cooler climate, that the cold side is colder, but I would have to do some more research. Yeah.
Graph that showed the drop in fuel economy was tied to the weight of the vehicles.
Yeah.
I've heard a lot of excuses as to why the weight of the vehicles is going up. One of the most prevalent one is, well, it's safer to have a bigger car. That, unfortunately, is not logical because there are all kinds of methods that you can use using different materials, for instance, that would still make a car as durable
Yeah.
as the higher weight car, but dropping the weight down. And do you have any idea why that strategy has not been followed?
reducing the size of the car. And that's a preference. But certainly, yeah, having lighter materials. So in the APS report, there's a big section about lightweight materials for cars. I think that sounds like it's a thing that's...
So this had,
Yeah, the APS report is really excellent.
that,
I can get the first for you. Yep.
You were talking about the efficiency of a system with 2 engines. How does that change if you add more engines, say like 3 or 4 heat engines linked together?
Yeah, so in that case, the argument for that would be, okay, so say you have a jet engine that likes very high temperatures, and you have a steam turbine that likes lower, and then you have some other thing that uses even lower grade heat, like thermoelectrics. Like, there could be some option for that. And the advantage of being able to do something like that would be that you could extend the temperature range. And you can derive analogous formulae for how the efficiency of that device operates. But again, as you continue to add them, you're still going to be subject to the kind of efficiency of the very highest to the very lowest temperature available. Yeah. Great, so we're at 12. I'm going to take questions. Oh, over here.
How's that Dunkin' bird work?
How's the bird work? Okay. It's a little bit complicated. So, so the inside there's a solvent, and the head has a sponge around it, and when it dumps in the water, it picks up a little bit of water, and as it's swinging, the water evaporates, and it cools the head, and as the head cools, the solvent condenses in the head, and that reduces the pressure in this tube, and this tube draws liquid out from the bottom guy, and then that liquid goes into the head, and then the head is heavier, and then it falls back into the water. And then the tube is arranged such that all the liquid flows back out, and it pumps back up, and then it cools and reheats. But it's really pretty subtle heat.
So where is, it keeps going indefinitely. The room gets colder?
Yeah, so what's the hot side and what's the cold side?
Yeah.
Yeah. So the hot side is the water. The cold side is the sponge on the head. So through evaporation, the T cool is the sponge, and the T hot is the
Did you talk about stirring engines?
Oh, I wasn't planning to. It is a very interesting design engine. I think it's mostly meant for specialized applications. So, we can talk about that.
Yeah, I'm using it for pumping water in India, so.
Yeah.